Welcome to the 77th Theoretical Physics Colloquium by Professor Yuri Kovchegov from Ohio State University. He got his PhD from Columbia University in 1998, had several postdoctoral positions at University of Minnesota and Brookhaven National Lab before receiving a research assistant professor at the University of Washington, where he spent 4 years between 2000 and 2004. And then he moved to Ohio State University, where he is there since. He's a full professor since 2012. Over the years, he received several prestigious awards, including in 2006, the Raymond and Beverly Sackler Prize in the Physical Sciences from Tel Aviv University in Israel, and he became a fellow of the American Physical Society in 2012. Over the years, he also was deeply involved in professional service, including being the member of the EIC white paper, the steering committee, and he is a member of the International Advisory Committee for the Center for Frontiers in Nuclear Science since 2017, which is at Brookhaven, Stony Brook University, sorry. His research interests include particle and nuclear physics, quantum chromodynamics, deep inelastic scattering, high energy evolution equations, small x physics, ultra-relativistic heavy ion collisions, physics at electron-ion collider, and probably many other things. And today he will be talking about small x contribution to the proton spin puzzle. And with that, I'll give the microphone to Yuri.
All right, thank you very much for the invitation and for the introduction. And I'm gonna start sharing. Okay. Let me just, make a few adjustments here. I would like to have, the chat window up. Okay. Please feel free to interrupt me at any point if there are any questions. Yes, and Igor is sharing the policy on questions, so that I subscribe to that, I guess. But in general, since with those online talks, the audience, sometimes you don't know who the audience is, so it's really hard to gauge the talk properly. So I would appreciate feedback from the people with questions and comments. All right, anyway, with that being said, I'll talk today about trying to tackle the so-called proton spin puzzle, used to be known as the proton spin crisis, and I'll concentrate on the small x contribution to that puzzle, and I'll describe the recent progress that my group has done over the years. So my talk will be based on on the work with the people listed in this on this slide. You see quite a number of people have contributed. All right, so the outline of my talk is shown here. I'll start sort of in a very general colloquium mode. Again, Igor asked me for a colloquium tailored for graduate students, and this is where we're going to start. I'll talk about deep inelastic scattering and also about the electron-ion collider that is going to be built in the US in the next decade, over the next decade. Then I'll give an introduction to the proton spin puzzle, what it is, why it is interesting and important. And I'll kind of outline our strategy in tackling at least the small x part of the proton spin puzzle. And then maybe I'll go a little bit more for the expert level and describe specifically how we tackle quark helicity at small x. And the way we do it is we work with so-called polarized dipole amplitudes, and we write small x evolution equations for these polarized dipole amplitudes, which then give small x asymptotics for the quark helicity. So I derive essentially new evolution equations in that part, and then I solve these equations in the next part and describe how we can do phenomenology for various polarized deep inelastic scattering observables using this small x, new small x evolution. And that would also allow us to estimate how much of the proton spin is really at small x. And if I have time, which is not likely, I'll also flash the results for other quantities like gluon helicity and quark and gluon orbital angular momenta at small x. So our technique is not just for quark helicity, it applies to other distributions as well. And after that, I will conclude. Okay, so the introduction to deep inelastic scattering and the electron-ion collider. Deep inelastic scattering, the concept of deep inelastic scattering is very sort of straightforward and simple, right? If you want to learn a structure, probe a structure of a complicated object, such as a proton or maybe even a nucleus, what you do is you send a tiny small particle through it, like an electron, for instance, to probe the structure, to understand what the proton is made of. And okay, this is a more artistic rendering for deep inelastic scattering. This technique dates back to Rutherford and famous Rutherford experiments of shooting alpha particles, for instance, at the gold foil or the gold nuclei to understand the structure of to understand the structure of the gold atoms. And of course, we can go back in history and imagine, not just in particle physics, and come up with other examples. So the idea again is you send a small probe through a complicated object to learn its structure. Here is a movie of deep inelastic scattering. Again, this is a colloquium. This is one of the movies produced by Brookhaven National Lab in preparation for EIC. Maybe I should play it one more time because it goes rather fast. The electron comes from the right, say the nucleus from the left, they collide, and in the process probe various properties of quarks and gluons inside the nucleons. Okay, so here's an example of a deep inelastic scattering event as was measured at the Hera collider back at Daisy Lab in Hamburg, Germany. Hera operated there throughout the 90s and early 2000s. So here you can see a positron, not an electron, but a positron coming from the left, a proton coming from the right. They collide in the middle, and then an electron, the positron comes back out, recoils, and the proton remnants of whatever the proton was broken into come out through the detector here. DIS experiments have been done over the years. They started back in the 50s and 60s at SLAC and CERN, and more recently were done at Hera, that I already mentioned. Deep inelastic scattering experiments are currently running at Jefferson Lab at lower energies, and there's also DIS experiments at CERN, the COMPASS experiment that is, I believe, running currently, or at least very recently has been running. Now, in the future, there are proposals for more deep inelastic scattering experiments. There are proposals in Europe to build LHEC after LHC at CERN, so collide electrons with protons or nuclei in a CERN ring. In China, there is a proposal for an electron-ion collider. Lower energy electron-ion collider is being considered. Very recently, or reasonably recently, U.S. Department of Energy approved the future construction of the electron-ion collider in the U.S., and it will be built at Brookhaven National Lab. Just to give people a little bit of a background about the electron-ion collider and the physics it will probe, I just want to give a little bit of recent history here. Electron-ion collider, the idea was born sometime in mid or late 1990s. The concept of sort of utilizing maybe ring after ring experiments would be done to collide protons and nuclei with electrons. And so that idea surfaced in 1990s. There was a number of workshops in late 90s and throughout 2000s dedicated to that physics. An important milestone in the development of the case for the electron-ion collider was the electron-ion collider white paper, which I think Igor already mentioned in his introduction. It was written, the first edition was in 2012, the second edition in 2014. It's an effort by quite a number of people trying to make a science case, a comprehensive science case for the electron-ion collider physics. And at that time, there were two labs which were competing for the electron-ion collider. One is Brookhaven, and another one is Jefferson Lab. This white paper paved the way for the long-range plan in nuclear physics, 2015 long-range plan, which resulted, so nuclear community goes through this exercise every 5 or 7 years or so of making long-range goals for the future in the US. And this is one of the recommendations, recommendation 3, and you can see highlighted at the bottom that we recommend the high energy, high luminosity polarized EIC as the highest priority for the new facility construction following the completion of FREEB. So that was a crucial milestone in the development of EIC, the fact that it made it into the long-range plan. There were other milestones. I'm not trying to give a comprehensive review here, just to give people some background. One was another important step was a National Academies review, which gave a stamp of approval and resulted in this report. You see the cover of that report in the upper right of the slide. And that happened a few years after this long-range plan, so it was in 2018. And then in January of 2020, as it turned out, just a couple of months before the lockdown started, DOE announced that EIC will be built at Brookhaven National Lab. And actually a month before that, in December 2019, DOE gave a CD0 Critical Decision 0 to this project. Since then, the project has been developing rather fast. In July of this year, we got CD1 Critical Decision 1, so it's on track in terms of where it should be in its development. All right. What are the physics topics, right? So this was all just a bit of history. What are the physics topics we want to study, say, at EIC? We want to study the spin and nucleon. So the topics really fall under two categories. One is QCD in a single nucleon, and another one is QCD in a nucleus. In the QCD in a single nucleon category, well, it goes kind of like spin under spin and nucleon structure topic. One can talk about the spin of a nucleon, and this will be really ultimately the topic of my talk today. One can also talk about transverse momentum distributions, the so-called TMDs or TMD PDFs. And if you're interested in spatial imaging of quarks and gluons in space, one looks at generalized Spartan distributions, GPDs. And EIC would have such a high luminosity that all these quantities will be measured with unprecedented precision over a fairly broad range of the kinematic space. Now, QCD in the nucleus is another big topic, like I said, and the subtopics here are looking for high gluon densities and parton saturation, which could be a topic of a separate talk, but I'm not going to talk about it today. One can also talk about quarks and gluons and how they interact with each other in a nuclear environment, whether they're still confined within nucleons in the same way as in a free proton or not, and connections to various other collider experiments, proton nucleus, nucleus, nucleus collisions, and even cosmic ray physics. So these are the topics, and highlighted here again, spin of the nucleon is the topic I want to talk about today. So DIS, again, at a very introductory level, DIS process is pictured here. We have an electron come in, a proton come in, they interact, and the electron, of course, doesn't interact strongly. The only way they can interact is by exchanging a photon, and the virtual photon here, and the photon interacts with one of one of the quarks in a proton, knocks it out of the proton, and breaks the proton apart. This is really the process. The resulting quarks and gluons hadronize, becomes mesons and baryons, and go off into the detector. Electron also recoils, as I showed in one of the earlier slides, and also can be and is measured in the detector. So the process really, in much of my talk, I'll forget about the electron part here. We'll talk about a virtual photon scattering on a target, which could be a proton, or in principle a nucleus, but I'll mainly talk about the proton. The relevant parameters here are the virtuality of the photon, right? This is a internal line in the Feynman diagram, so it's a virtual photon. It's a space-like photon, so negative for momentum squared is the virtuality q squared. And the quark that gets hit in the proton carries a fraction x of the proton light cone momentum. So you can think of the proton being a very high energy proton going along the light cone, and the fraction x of its light cone momentum would be carried by the quark that would be struck by the photon and knocked out. So this fraction x, or xbj, is known as a Bjorken x variable. So everything I'll talk about today will be in terms of q squared and this x variables. The physical meaning of those variables are as follows. You can just use the uncertainty principle to argue that if you have a photon with virtuality q, it will be probing transverse distances inside the proton of the order of 1 over q. So this is kind of a cartoonish representation of a proton here. If those little blobs are quarks and gluons, the photon probes distances on the order of 1 over q. So what we mean by those virtuality q really, it's related to the distance probed. So for instance, if we want to probe shorter distances inside the proton, we need larger momentum q. So large q means short distances probed, and vice versa. Low q means larger distances probed. So if you wish, this is some sort of a magnification in the like in the microscope, right? If deep inelastic scattering process is a way to probe the proton under a microscope, q is a magnification of that microscope. The physical meaning of Bjorken x is shown here in some detail. So suppose we have a proton that comes in with all the quarks and gluons in its wave function, and one of these, say, quarks here interacts with a target. One could argue, again, on very general grounds, that the momentum of this quark should be sort of comparable to the momentum of some target. So if the quark here carries momentum x Bjorken times p, it's comparable to some momentum q in the target, call it m or whatever. Then you can show that the energy of the collision, which is the momentum of the proton, right, in the rest frame of the target, it should scale as 1 over x. So bottom line is high energy corresponds to small x, and vice versa. Lower energy collisions correspond to higher values of x. All right. That's that. That's the two variables here. What do we know about the proton structure? And this is a bit of a summary of unpolarized, so spin-independent proton structure we know from the Hera experimental program. So what's plotted here is a so-called Parton distribution functions, q of x and q squared and g of x and q squared. They count the number of quarks and gluons, or the number density is counting the number of quarks and gluons inside the proton as functions of x and q squared. They're plotted here as a function of x. And on the vertical axis, we have those Parton distribution functions times Bjorken x. So this is x times quark and gluon Parton distribution functions as a function of x. X, of course, has to be, it's a fraction of the proton momentum. It has to be less than 1, and it is positive in our notation. So it varies between 0 and 1. This is a log scale, doesn't go all the way down to 0, clearly. What you see here is the valence quark distribution, say up and down valence quark distributions. They are shown here. Remember, proton is made out of 2 up and 1 down quarks. And then you have a gluon distribution and C quark distribution, denoted by the letter capital S. And we see from this picture already that there's a lot of quarks and gluons at small x, right? A small Bjorken x variable values inside the proton. So what we know is that from this plot is that at larger x, the valence quark distribution is dominant in some region, or at least quite competitive with gluon and C quark distribution. But at small x, things are actually quite different, and valence quarks are not so much relevant. You only have C quarks and gluons which dominate at small x. So this is just sort of a qualitative, well, it's a quantitative statement, of course, but it's also a qualitative picture. The question is, how does it come about if the proton is made out of 2 up and 1 down quarks? Well, the way qualitatively we understand this is, of course, you don't just have 3 valence quarks in the proton. They can emit gluons, so the wiggly line is a gluon. The gluon can split into quark-antiquark pair, into more gluons, and that's how we create additional C quarks and gluons inside the proton. Okay, so that's a qualitative understanding of this picture from Hera, from the combined Hera fit. Okay, very good. So do we understand everything? Of course, we don't understand everything here. That was just a hand-waving qualitative explanation. But specifically, let's talk about one aspect of our understanding of the proton, the so-called spin puzzle. And let me continue with an introduction. Should I pause, Igor, for questions if somebody has any? I don't
so far I didn't see any questions coming up. But since you already kind of interrupted it, I actually kind of had a small question regarding the EIC. Maybe you will return to this, so if that's the case, you could postpone it. But the question was very simple. I kind of understand why it's kind of high precision measurements that could be very useful. But there was also this statement in the general, I believe, white paper saying that there is also wide versatility of the EIC experiments. I'm not quite sure what that versatility truly means, if you have something that may clarify.
Okay, I might have, I have been on the steering committee for the white paper, but I hope you don't expect me to remember every sentence. So I'm not sure what context it was in. By versatility, I guess people could mean several things. One is that, for instance, you can, I don't know which slide I should show. Yeah, the white paper. You can run several different nuclear species, for instance, right? So you can do deep inelastic scattering on a proton, on a light type nuclei, and heavier nuclei, and some intermediate nuclei. So there is certainly, you can do a scan in terms of the atomic number sizes, something, for instance, Hera never got to doing. You can also,
versatility in terms of the types of the systems, then probably.
I believe that's one way it could be, could have been said. Another one is, I believe there would be an option to vary the collision energy, so that also provides additional versatility in terms of maybe doing more precise higher X measurements.
Okay, that's fine. That's fine. I understand. It's not like the most critical question anyway, but somehow that kind of thing stood up to me, and I was wondering if there was something deeper than I thought.
No, I think those are some of the aspects. Actually, in addition, I'm forgetting there's also polarization, right? You can have longitudinally polarized protons, for instance, and transversely polarized protons at the EIC. You will have, I should say, in a future tense, I don't believe Hera could ever do transversely polarized protons, for instance. Rick can do transversely polarized protons now, but they're not a DIS machine. They just collide protons with other protons. But I don't think Hera could ever polarize protons transversely. So there's a lot of, things that other DIS experiments just couldn't do, and AIC will be able to do with, in addition, with much higher precision.
That's fine, thanks.
Okay. All right. If there are no further questions, let's move on. So what is the proton spin puzzle? Yeah, sorry, let me just jump to wherever I have that slide. So, the puzzle in a nutshell is the following. The proton is a fermion with spin 1/2, right? We know it has spin 1/2, but we also know that it's not a point-like particle. It's a composite object made out of quarks and gluons that we just discussed to some degree. So the question is, how is the spin distributed among those quarks and gluons? Well, you say naively, say if you picture yourself back in the 70s or 80s thinking about it, constituent quark model was very, very successful at that time, described a lot of different data. Why not say that, you just have 3 constituent quarks? This is the picture on the left of this in this slide. You have 3 constituent quarks, 2 of them spin up, 1 spin down. That's it, right? That's the end of story. Well, what you'll see, and I'll show it in the next few slides, is that this is a great theoretical prediction, but it just didn't work if you in the experiments, right? People looked at the spin carried by quarks in the proton, and they found something much less than 1/2. And the result is that our present picture of the proton spin is much more nuanced. People don't really believe that the proton spin is carried by only one specific source, like the spin of the quarks. The proton spin now is believed to be made out of spin of the quarks, spin of the gluons, spin of the C quarks, not just valence quarks, so as well. In addition, there is orbital angular momentum, which can be carried by either quarks and gluons. So all these 4 components, spins of the quarks, spins of the gluons, and orbital angular momentum of quarks and gluons, contribute to the spin of the proton. And the goal is to identify what those contributions are and how they add up to give us 1/2 the spin of the proton. So I think that's a fairly fundamental and interesting question about the spin structure of the proton. So how do we quantify those statements? We quantify them in terms of helicity distributions. So I talked a little bit about parton distribution functions, which just number densities of quarks and gluons regardless of their spin. But you can also define number densities which depend on the spin. So you can, for instance, count and take a proton, a polarized proton. So a circle here with an arrow is a polarized proton. You can count the number of spin up, say quarks, in that proton minus the number of spin down quarks in the proton, and that would give you the so-called helicity distribution. So delta F could be number of spin up minus number of spin down quarks or gluons. So F could be up, down, strange, whatever. And delta G, defined similarly if F is G, is the gluon helicity distribution. In my talk, I'll also talk about the so-called flavor singlet quark helicity distribution, which is a sum of helicity distributions for all the light quarks and antiquarks together. So with the help of this helicity distribution, right, so it really measures the degree of polarization of quarks or gluons in a polarized proton. The statement of proton having spin 1/2 can be formulated in the form of the helicity sum rule, and this is the helicity sum rule due to Bob Jaffe, who is actually in the audience, and Anish Manohar, written back in the late 80s, which says that the spin of the proton 1/2 is the sum of the spin and orbital angular momentum of all the quarks in the proton and spin and orbital angular momentum of all the gluons in the proton, where the spin contributions can be written as integrals over this Bjorken x variable of the corresponding helicity distribution. So delta sigma, remember, is the quark helicity distribution. So you integrate it over x, and you have to multiply it by 1/2 to get the spin of the quarks. And the spin of the gluons, to calculate that, you take delta g, and then you integrate it over all x as well. LQ and LG are orbital angular momenta. You can also write them as integrals over x, but that we'll do later on in our discussion. So, people often represent this sum rule as a pie chart, right? So you have different ingredients composing 100% of the spin of the proton as individual segments of this pie chart. Okay. So constituent quark model expectation I already mentioned, right? If you have just 3 constituent quarks, 2 spin ups, 1 spin down, it just says, okay, all the proton spin is carried by the quarks, and then you have SQ equals 1/2, done. Well, the experiments back in the late 80s, the European muon collaboration measured the proton G1 structure function, and the data could be translated. Well, they didn't measure SQ directly, they measured G1 structure function, but the data could be roughly translated into SQ of the order of 0.05. Remember, if quarks carried all the proton spin, SQ would have been 1/2. So one got roughly an order of magnitude less spin carried by the quarks. The number is higher now. SQ is not as low now as it, I guess, was originally measured, but nonetheless, that posed a problem, or a crisis as it was called, and that was the beginning of the proton spin crisis. Now, where can the missing spin be? Well, you look at the Jaffe-Manohar sum rule, right? You have all these different sources of spin. Spin can be carried by gluons, can be carried by orbital angular momenta of quarks and gluons. And in addition, and that would be the main thrust of my talk, it can come from the small x region of those integrals. So when we say that the quark and gluon spin are integrals over x of the helicity distributions, the integrals go down, strictly speaking, to x equal to 0. But in reality, remember, low x corresponds to high energy, so x equals 0 corresponds to infinite energies. No experiment ever has infinite energy, so no experiment can measure the helicity down to x equals 0. So instead, they measure it down to some x min, which is determined by the acceptance of the experiment. So, yeah, question?
There is a question from Giorgio Torieri.
Oh,
Yeah,
I'm sorry.
I just wanted to ask. I mean, the sum rule, the left-hand side is gauge invariant, but on the right-hand side, you can choose gauges that move things around, right?
Yes.
In this version. I mean, this, to a certain extent, all of these are gauge-dependent statements, right?
It's a little less. It's not quite as lax. So in principle, yes, but instead of, so you can make all these quantities gauge invariant. Oh, I'm sorry, I'm hearing my own echo. You can make all those quantities gauge invariant, but to do that, you have to put a Wilson line. So you define. So this is getting maybe a little technical, but the question is, when you define Parton distribution function, you define a correlation function, a 2-point correlator of quark or gluon fields. And as such, of course, since it's a non-local 2-point function, it's not gauge invariant. So to make it gauge invariant, you put some sort of a gauge link. And then depending on how you put that gauge link, you may have a freedom. Well, you have a freedom in the path, right? So the gauge link path could be a straight line, could be something more complicated, like going off to infinity and coming back. That's kind of good for deep for CDIS processes where you actually produce something. So bottom line is, instead of gauge invariance, you have dependence on the path. But if you stick to a specific convention, so certain definitions with a certain shape of the path connecting the 2 points are easier to measure. So if you stick to that convention, everything is well defined. Am I making sense, or maybe should I draw something?
Giorgio, you're fine? Should we move on?
Yeah, I think so. Yeah, thanks.
Well, I was just gonna annotate. I don't know. It's always a little risky somehow when I self-annotate. So you have a 2-point function. You can have a Wilson line which just connects 2 points, or you can have a Wilson line, for instance, that goes off to infinity and then comes back. So the quantity is gauge invariant, but then you have uncertainty at what path to choose. But if you agree on a certain path convention, it's all well defined. But yeah, of course, there are other ways also. So depending on this path choice, you may actually, well, this is a modern understanding, I guess, that depending on the path choice, you may write different sum rules. There's also a G sum rule that I didn't have the time to mention. And there are also kind of like all the various in-between sum rules you can construct just by varying the shape of this path. But again, once we agree on a certain path shape, then it's all good, and we then it's all well defined.
Okay, thanks.
Okay, yeah, okay. So moving on. So if the experiments go down to some x mean, there's always going to be some uncertainty, right? How much spin is at yet lower x the experiments have not measured. So it seems like, it seems like we need to have a theoretical tool to extrapolate, not just kind of by hand, but theoretically extrapolate the experimental measurements down to x equal to 0. And constructing this tool is really the goal of this research program that I'm talking about. Now, the current knowledge of the proton spin, of course, has improved since the EMC days of the late 80s. Nowadays, we know that the quark spin is somewhere between 0.15 and 0.2. I guess a number on order of 0.17, 0.18 is usually quoted. Notice that this is in a given x range. The gluon spin has been measured recently. They extracted it from the data, mainly spearheaded by the STAR data, but of course including COMPASS and Hermes data, with a number in this range. 0.2 is roughly the number that's usually quoted. You see still, if you take 0.2 and 0.18, you're not getting 0.5 yet. And there's also uncertainties at small x, right? Because there are these numbers are all measured down, as I said, to some non-zero value of x, and you can go yet lower and find more spin there. So how is this number extracted? Usually it's extracted using the so-called Deglop evolution equation, the Dorchester-Gribov-Lipatov-Altarelli-Parisi equation, and I want to spend a few minutes explaining how this is done and what the advantages and maybe shortcomings of this approach are. So the Deglop evolution is a renormalization group equation in the q-squared scale, in the resolution scale. And roughly it can be formulated like this. You have a Parton distribution, you change the resolution scale. As you change the resolution scale, you get corrections. You can think of it as changing the phase space and generating more partons emitted in that phase space. Or diagrammatically, it's really just this. You have corrections to your PDF. Or say this is a real correction, you have virtual corrections as well. In the end of the day, when dust settles, and I'm talking here about the spin-dependent, helicity-dependent case. So helicity-dependent Deglop equation. There's of course also unpolarized Deglop equation, but helicity-dependent Deglop equation is shown here. You have the quark and gluon helicity distributions, which, as you differentiate them with respect to q-squared, can be related to themselves as well, with some integral kernel given by the so-called splitting functions. In the exact shape, the exact form of those splitting functions is not terribly important for us today. Okay, fine, great. You have an equation. What do you do with this equation? How does it work, first of all? It's a renormalization group equation, which says as you go to, so say you view the proton at some initial resolution q0, and you can resolve, remember, lower q0 means larger distances, you resolve some partons in the proton, and then as you increase the virtuality q, you're probing shorter distances, and you see that what may have looked for you as a single particle really has some structure. So each of those blobs has more of a substructure in it, and this is a meaning of Deglop, right? You really just increase your resolution. If you wish, you integrate out all the low momentum, larger distance degrees of freedom, and you see more and more partons at larger q squared. For the students in the audience, this is really, say, the what I'm talking about is a cover of the well-known book by Peskin and Schroeder, right? Here you can see that as you zoom into the, say, if this was a proton, you zoom in there, you see that you have maybe valence quarks and the gluons, and what it seems like just a valence quark for you, if you zoom into it, is actually a quark dressed by more gluons. Each gluon is dressed by quark antiquark pairs, whatnot. So really, this is what Deglop does. It's just a renormalization group. Well, it is a renormalization group equation. How does it work in practice? Well, in theory, it's a first-order differential equation in q squared. That's why it's called an evolution equation, because it kind of looks like Schrodinger equation with log of q squared being time, and some Hamiltonian, some effective Hamiltonian. So what it does is you specify the initial condition at some q naught squared. Initial conditions are a function of x, or here it's log 1 over x. And then you evolve, you solve the evolution equation, and you get solution at all other q squared, right? Q squared larger than q naught squared. This is how Deglop equation works. You have to specify the initial conditions. In practice, you kind of have to measure the initial condition. And then you get the solution, PDFs at all x and q squared. Now, in practice, of course, you have some data to fit. So what people do is they parameterize the initial condition. They don't specify the initial condition. They just specify some functional shape, functional form of the initial condition, and then they fit the data by varying the parameters in their initial conditions until they can fit all the data, and then they say, okay, well, we know what the initial condition is, so therefore we know the PDF everywhere. There is a problem with the Deglop approach, namely that it's a differential equation in q squared. It does very little in terms of predicting x dependence, right? So ultimately you parameterize x dependence in the initial conditions and you fit it to the data. Of course, Deglop evolution does affect your x dependence, but to a degree. Certain initial conditions can also dominate x dependence of Deglop. So the x dependence you get from Deglop evolution from this approach is not predicted, and therefore Deglop evolution cannot predict how much spin there is at small x, right? It tells you what happens at higher q squared. It doesn't tell you what happens at small x, which would be up on this plot. So Deglop equation is not going to help us in our quest to understand how much spin there could be at small x. So, and this is manifested in the following plots here, diagrams, well, not diagrams, but plots. So what's plotted here is a spin carried by quarks and by gluons as a function of this x mean parameter. So if you look at the axis, right, we have this delta sigma integrated from x mean to 1. So on the left panel, so this is twice times quark spin, and x mean is that effective cutoff. And you see that the error bands start exploding as x mean gets lower. You can see also an improvement. The error bands don't explode so much with newer rig data, and maybe with EIC data coming in, they'll get even narrower, but still you get a decent error band. Notice that at this value of q squared, this is at q squared of 10, most of the world data is above of x to the 10 to the minus 2, right? So you see that once you go outside the region where the data exists, the error bars explode in this extraction of PDFs based on Deglop approach. And this is again because Deglop cannot predict how much spin there is at small x. The situation for gluons is even more complicated because there's fewer data points which constrain the gluon helicity distribution, and you can see that the gluon PDFs are also exploding at small x mean, rather very much so, right? So really there is a need for some theoretical way to constrain all those arrow bands. Of course, EIC will come and narrow those arrow bands, as you see in the darker shades of blue here, and make things better. But as you'll see also in my later plots, some of these problems will still persist after EIC unless the theory, unless there is some theoretical improvement in the current status. And at small x, again, remember we were discussing at small x, the physics is different because it's dominated by C quarks and gluons. So that's the regime we would like to tackle and understand how much spin do these guys carry, really, and whether we can predict this theoretically. Okay, so our goal in this work, well, whatever 10 minutes time I might have left, our goal is to understand how much spin, quark and gluon spin, and orbital angular momenta comes from small x. Again, at very small x, we expect saturation to set in, and that's a topic for a separate talk on a separate on another day. But there, at least naively, we expect to find very little spin. But in between, at small x, but still outside the saturation region, there might be a significant amount of the spin, of the proton spin, hiding there, and that's really what the message of my talk, one of the messages of my talk, will be. So the philosophy is, as I convinced, hopefully, the audience, that Deglop doesn't evolve in X, it evolves in Q squared. And the Deglop-based analysis, I showed DSSV, but there are other ones, and then PDF, JAM. They cannot predict X dependence of PDFs or Helicity PDFs in question. But what we need is an evolution equation in X, which will tell us X dependence of Helicity PDFs, at least from the theoretical expectations. And such equations have been constructed by Dan Pitoniak, Matt Sievert, and myself over the 3 years here, shown here from 2015 to 2018, using an approach similar to unpolarized evolution equations like BFKL, BK, and GMWalk. So just to give you an idea of how BFKL works, it's sort of in some way similar to Deglop, but in other ways it's different. BFKL equation is an evolution equation in X. It really says that, well, if we have a proton with, say, n gluons, which are shown for simplicity by straight lines here, as we increase energy or decrease Bjorken X, right, that's equivalent, we can emit an additional gluon from all the pre-existing gluons. So the change, say, in the number of gluons, so as we differentiate with respect to log 1 over x, is proportional to the number of gluons. And instead of the coefficient of proportionality, we have some integral kernel here, which, again, I'm not going to show because it's not terribly relevant. And this is, of course, a very important equation and a topic for a separate talk. But the idea is to construct something similar for, this time for helicity. So this is what we did sort of at the colloquium level view. We say, okay, suppose we now have a proton, but a polarized proton, which has quarks and gluons in its wave function. And again, we increase the energy. And we can tag on a polarized quark or on a polarized gluon. And as we increase the energy, we get more phase space, so we can emit a new polarized quark or a new polarized gluon from the pre-existing quarks and gluons, and measure the polarization of those guys, and then we'll know, essentially, if we keep iterating it, we'll know what the helicity distributions are at small x. So this is really the main concept of the helicity evolution I'm about to construct, maybe in a bit more technical details, but the idea is to evolve, to write a differential equation in x rather than in q squared. So this is also summarized in this chart in the lower right corner of the slide. This is a log x, log q squared plot. So q squared x is, sorry, not a log q squared, but just q squared, log x q squared plot. Q squared axis is a vertical axis, so Deglop evolution works upward. I was showing it before evolving left to right. Now it evolves, bottom to top. If we're interested in knowing how much spin there is at small x, we want to have an evolution which goes to the left, and this is what Dan Pitoniak, Matt Sievert, and myself have constructed. Okay, should we pause for another questions? Because things are about to get a little bit more technical now.
I don't see any questions in the
Okay.
reactions, so maybe you should proceed.
Okay. All right, so the way things work out, so let's talk about quark helicity at small x specifically, and let's talk about deep inelastic scattering again, maybe at a more detailed level. So if we're looking at deep inelastic scattering at small x, deep inelastic scattering is described, say, by the correlation function of two electromagnetic currents, right? At small x, a small Bjorken x, or say at high energies, you can argue that, say, if you're so you can forget about the electron. You have a virtual photon scattering on the proton, and the virtual photon-proton scattering is shown here, and the virtual photon at some point has to interact with quarks, and you can just do a simple estimate that if you're a small x, if you're Q minus, light cone minus momentum of this virtual photon is sufficiently large, that means the plus momentum of the photon is low. That means that the minus separation between those two electromagnetic currents, which are the vertices between the photon and the quark interactions, should be very large, right? So your minus separation between those two currents will be large, much larger than the proton size. So therefore, that picture where the photon comes into the proton and knocks out a quark no longer applies here at small x. Rather, you have this dipole picture where the photon comes in, splits into a quark-antiquark pair before interacting with the proton. So it's a quark and antiquark pair, a dipole, made out of quark and antiquark that interacts with the proton, and then that dipole recombines back into the photon if you're interested in the forward scattering amplitude and therefore the total cross-section. Another way of saying the same thing is the picture I showed before of a deep inelastic scattering is shown here. This is amplitude squared. It's kind of upside down compared to what I had before, but really the photon just comes in, knocks out a quark out of the proton, and that's it. And then you have to square this amplitude here. This is the standard handbag diagram, as it's called. What I'm saying is at the small x, this handbag diagram is actually not the dominant one. Rather, you have this process where the photon comes in, splits into a quark-antiquark pair. The dipole, quark-antiquark dipole, interacts with a proton, and then, for the forward scattering amplitude, it recombines back. One can argue that, well, but this is higher order in alpha s, right? You can, in principle, imagine that there are like two gluons exchanged here, and then if you count the powers of alpha s, you would see that you are sort of a higher order in alpha s compared to the first handbag diagram. This is all true, but at small x, this second diagram has an extra 1 over x, so the dipole picture dominates at small x because the suppression by alpha s is really wiped out because you have this extra 1 over x factor. So that's sort of the philosophy, the general philosophy of the dipole approach. Let me erase all this. In practice, so deep inelastic scattering then reduces to a dipole scattering on a proton. Now, suppose we are interested in the scattering which depends on the proton polarization. So suppose a proton is polarized. So this is a picture here. We have a nucleon, proton, neutron, whatever, which is polarized. And we have an electron emitting a virtual photon, producing quark-antiquark dipole, which interacts with this proton. And we want this interaction to be dependent on the polarization of the proton, right? We're interested in spin dependence and helicity distributions. So the standard small x evolution, non-polarized small x evolution, doesn't care about spin, and one just simply takes high energy scattering of this quark and antiquark with a proton, which is actually spin independent. But spin dependence shows up when you allow for corrections to this simple picture to come in, the so-called subiconal corrections, which are suppressed by a power of energy or correspondingly by a power of Bjorken x, a small x, but nonetheless they may not be terribly small. So one can argue that the helicity distribution, delta sigma, is related to this object which we call the polarized dipole amplitude, which is an amplitude for a dipole, quark and antiquark dipole, to scatter on a proton. The dipole has a size, transverse size, say R10. It has a longitudinal momentum fraction beta, longitudinal momentum fraction of the virtual photon, say carried by the quark in this pair, we can call it beta. So the dipole depends on this dipole size and beta, the dipole amplitude, and that's where all the strong interactions are. And you can write, I wrote a simple tilde. Of course, the expression is more involved, but it's a known expression which relates polarized quark PDF to this dipole amplitude. Okay, so what is this dipole amplitude and how we calculate it? The way we do it is, well, it's a dipole scattering on a proton, so it has to interact with a proton in a spin-dependent way, because we're interested in spin dependence. So we can write this schematically as we have a quark and antiquark lines. Say that if the quark is unpolarized, we write just a Wilson line for that quark. This is V sub 0. And say in this left panel, the antiquark interacts in a spin-dependent way, so its interaction with the proton is described by something called V polarized, or V polarized dagger, depending on whether you're on the left or on the right. This is sort of the first correction I mentioned. This is not the iconal propagation. This is not just a Wilson line, but it's a Wilson line with some sub-iconal spin-dependent interaction included. And double brackets correspond to scaling out energy suppression I talked about. This is a technical detail we can skip. So how do we construct this V polarized? What is this polarization dependent interaction of a high energy quark with the proton? Well, the way it goes is you just do a calculation. You imagine a high energy quark going through some background field, and all the interactions are iconal, described by the Wilson line, except for one special interaction which is sub-iconal and depends on polarization. So it transfers polarization information between the proton target and the incoming quark. Or you may also have another process where you exchange a pair of gluons with the a pair of quarks with the target in addition to all those iconal gluon exchanges, and the quark exchanges are actually energy suppressed and sub-iconal then. But these two diagrams are of the same order. Anyway, when dust settles, you get an expression like this, where you have those V's, which are Wilson lines. So you have two terms in this V polarized. The first term corresponds to the left panel. The second term corresponds to the right panel. What we have, say in the first term, we have a quark coming in, interacting iconally with a Wilson line with a background field. Then there is a non-iconal interaction, which actually turned out that it gives us F12, the 1, 2, or XY component of the field strength tensor F mu nu. And after that, again, we have just a Wilson line for the quark to go off to infinity. And then there is another panel with quark exchanges. I don't want to draw your attention to it at all. Just to give you, well, it's sort of, if you do want to pay attention, it's related to formal definition of helicity PDFs, but that is for the experts. What is this F12, right? Why is interaction of a quark with a target, the helicity spin-dependent interaction given by F12? Well, the physics of this is really clear, right? What is F12? F12 is related to the Z component. It's really negative BZ, Z component of the chromomagnetic field. So if we have a polarized quark interacting with some background field in a spin-dependent way, the interaction should be just given by the mu dot B operator, and that if mu is pointing in the Z direction is the direction in which the quark is flying, then it becomes mu Z BZ, and BZ is just related to F12. So it's very natural that we actually just get a mu dot B coupling here for the quark to the spin to the chromomagnetic field of the target, which depends on the spin of the target. Okay, so if we know our operators, we can write down evolution equations. This is a bit technical here, but maybe not terribly so. We have this dipole amplitude shown here. We increase the energy, we can emit various gluons or quarks, soft, small x, quarks and gluons. The rectangle here represents the proton or the shock wave going in the opposite light cone direction. So you can have various gluon emissions outside the shock wave and absorption outside the shock wave. The blob means this F12 subiconal vertex, that we have just constructed in this operator. So a lot of this evolution is very similar to unpolarized small x evolution, but the first two lines are new and are helicity dependent steps. Okay, so bottom line, it's a bit technical. I'll finish being technical in a few minutes. We get some evolution equations which are not closed, as an object on the left and object on the right are not the same, but one can take something called the Lagrange limit, imagine a large number of colors in QCD, and get a closed system of equations where we're interested in this dipole amplitude G. The evolution equation couples it to some auxiliary object called gamma, the neighbor dipole amplitude. So you have this coupled system of equations which you really need to solve for G. The initial conditions for these equations are given by Born level interactions shown here. So you have initial conditions, you plug them in, you solve these integral equations, you find G. If you know G, you can find helicity PDFs, you can find G1 structure function, whatnot at small x. And there is a resummation parameter here. Again, this is for experts. You get 2 logs of 1 over x for 1 power of alpha s, and this is known as a double logarithmic approximation. Okay, so if you have an evolution equation, great. What do you do with it? Well, you solve it to understand, to see what it predicts. That should give us the small x asymptotics of quark helicity, and you can also do some phenomenology. So here's a solution. The equations can be solved. First we solved it numerically, then actually we found an analytic solution. The bottom line, skipping the details, is that at least in this Lagrange evolution equations, the quark helicity distribution, say delta Q, comes out to be as 1 over x to some power, and the power is shown here. Numerically, we got 2.31 first, then it turned out that 2.31 is really 4 over root 3 times square root of alpha s and c over 2 pi. So this is a perturbative calculation. Alpha s, the strong coupling constant, is small, and this power is actually proportional to the square root of it, and that's related to the fact that we're doing this double logarithmic resummation, which is a leading order result here. Okay, you say very good, but does it describe any data? So what we did very recently, earlier this year, we joined forces with Wally Melnichuk and Nobuo Sato from JLab, and my student Daniel Adamiak was very much involved in that project. We looked at the polarized DIS data, not CDIS, but DIS, the asymmetries people measure, like A1 and A parallel. Those are spin asymmetries and scattering of polarized electrons and polarized protons. And they are related to the G1 structure function, and G1 structure function in turn is related to helicity PDFs for quarks that we talked about. And we looked at all their data at small x. Actually, small x experts in the audience would say that this is not a very small x. This is x less than 0.1. 0.1 is already quite a large x for us. But nonetheless, looking at the data, x less than 0.1, q squared not too low, q squared above the charm quark mass squared, so about 1.2 or 3 GeV squared, I think. We described all the data with those evolution equations we constructed using the initial conditions of this type, which were inspired by this Born level calculation. So in the end, we have 122 data points For two flavors, we can only have 8 parameters and describe everything well. If we want to have 3 flavors, we'll have 11 parameters, describe everything very well. Our chi-squared per degree of freedom is very close to 1. The original GEM Deglop based fit actually had a similar, even slightly higher chi-squared of 1.07. So as I already said, it seems like the data is described if you start the small x evolution at x0 of 0.1, which is remarkably high. You can see this is a sanity check. This is our chi-squared per degree of freedom as a function of x0, the point where we start our small x evolution. And if we get too ambitious and started at very large x0, our chi-squared gets very large and the fit quality, of course, deteriorates. So definitely small x formalism that we have works as small x and breaks down at large x. This is good. This is as expected. So this is our prediction for G1 structure function of a proton. So this is G1 as a function of x. Let's start by first looking at the blue, which is the Deglop based, the so-called DSSV result. The light blue is the current state of affairs. The uncertainty is increasing as we decrease x at low x. Remember, Deglop doesn't predict spin at low x. There is a really large uncertainty. Now there's also part of this yellow report activity that happened over mainly the previous year. People did an exercise where they included EIC pseudo data to see how much it would shrink the error bars, and that's shown by this darker blue band. So you see the EIC data at this q² of 10 would exist down to a few times 10 to the minus 4. So it narrows down the light blue band to darker blue band where the data will exist. But if you go to lower x where there will be no data even after EIC, the error band still blows up, right? Again, because Deglop doesn't predict PDFs at smaller x. So that's an unsatisfactory state of affairs. And our approach, though, in contrast, is shown here in red. So the lighter red is a current fit, and the error band is significant, but it doesn't blow up too much at low x. And you can see with EIC pseudo data, there is a thin red line. It's not a center line of our fit. It's what EIC will do to our fit. It will shrink the error band down to essentially almost being invisible on this scale. And we'll have a very precise extrapolation down to a very small x. We also can do various Helicity PDFs. So that was G1 structure function, remember, which is related to Helicity PDFs. We can also plot Helicity PDFs by themselves for up, down, and strange quarks. What we call delta Q plus in standard GEM notation is delta Q plus delta Q bar. In the lower panel, we plot delta sigma, which is, remember, sum of delta U plus delta U bar, delta D plus delta D bar, and delta S plus delta S bar. And you can see again the light blue is the DSSV, the darker blue is DSSV with EIC included, error bars still blow up at lower x, and the red is us with EIC pseudo data included. Our error bands are not doing much as we go towards lower x. So we should be able to predict how much spin is at small x if we're able to describe or even hopefully even better predict the EIC data. Then our results could be extrapolated down to lower x to describe how much spin is there. So question is, what do we have now? So based on those fits, how much spin do we anticipate to have at small x? So we constructed this quantity delta sigma x max, where we integrate from the lowest x we kind of generated in our approach 10 to the minus 5. It's a bit of an arbitrary number up to x max. So usually I was showing integrals from x min to 1. This is the opposite. This is from very small x to just regularly small x. And we plot this delta sigma x max as a function of x max, and you can see it gets quite big, right? On the order of 0.2, negative 0.2. Remember, we're talking about proton spin, right? So 0.5 is the spin of the proton. Delta sigma has to be divided by 2 to give the spin contribution. So negative 0.2 is negative 0.1 contribution to the proton spin. That's still 20% of the proton spin that can reside at small x. So that's kind of encouraging in terms of motivating us to look at this thing more closely. One can finally speculate a little bit about what these numbers mean. So remember I showed you the current numbers for quark and gluon spin, 0.18 and 0.2 roughly. A quark spin though is 0.18 if you look at x larger than 0.01. But we at least claim that we can predict what happens at lower x. So we can draw a line at 0.001. We can draw a line at x of 0.001 and see that our delta sigma is at about negative 0.2, delta sigma x max. So that means that 1/2 delta sigma is about negative 0.1. That's a negative contribution to the proton spin. That's good. That's not good. I mean, that's just deepening the spin crisis. But then there are works by Yoshihata and a collaborator, and I've checked it a year after, that the orbital angular momentum of small x quarks, actually, if you add it to the helicity distribution, you get negative 1/2 of the same helicity distribution at small x. So if you want to account for the orbital motion of quarks, you take this number of negative 0.2 and you multiply it by -1/2, and you get 0.1. So this is of course a wild speculation at this point, but at least it shows some plausibility that there's enough spin carried by quark helicities and quark orbital motion at small x potentially to resolve the proton spin puzzle, because you see the numbers we have is 0.18 plus for quarks, for large x quarks 0.2 for gluons, plus 0.1 for small x quarks. Altogether it comes out to 0.48, which is very, very close to 1/2. Okay, so I think I should finish because I apologize for running over, but it's all Igor's fault. He said there is no cutoff. EIC, of course, will come out, and this is a phase space diagram of EIC coverage for polarized DIS. And EIC and the dots are existing data. EIC will be able to probe much lower values of x than the existing data, and would be able to certainly help us complete the picture of the proton spin structure and narrow down delta sigma and delta G beyond what I've been showing. But hopefully we'll have, by the time EIC turns on, we'll have a more precise theoretical tools which will be able to either predict the data, or at least we'll be able to fit the data and then extrapolate down to lower values of x to constrain how much spin there is at small x, and resolve at least this sector of the proton spin puzzle, if not the whole puzzle entirely. So I apologize for running over. I'm going to skip some other topics I didn't have time to talk about and just jump to the conclusions. So the bottom line is we have constructed new, so skipping all the technical details, we have a new evolution equation which evolves helicity PDFs down to lower values of x. We can predict, therefore, x dependence of helicity PDFs at small x. It's been studied at large N C. I showed you there's also another limit, large N C and an F, where the equation becomes closed. I haven't had any time to describe this, but those studies give us small x asymptotics of quark and gluon helicity PDFs and orbital angular momentum distributions. But also, based on this equation, we constructed the first successful fit of polarized world data using only small x evolution, and that's what I showed you in the last few slides. And of course, in the future, we've already improved this equation. There are corrections calculated, and in the future, hopefully, the improved evolution will also be put to a phenomenological test, producing more precise fits and maybe constraining the spin at small x even further. So with a goal to eventually resolve the proton spin puzzle. Okay, thank you very much, and I'm going to stop here.
Thank you. Thank you for a nice presentation. We will have some time for questions now. Oleg Turev, you are the first.
Okay, thank you very much, Yuri, for this interesting talk. And I actually have a couple of questions. And the first one is coming from the old times of the double log evolution of G1. And at that time, I was puzzled by such a simple fact. That if you take unpolarized evolution, BFKL, there is no double logs. It's only single log, double are cancelled. And because double logs is larger than single log, it seems that, just naively speaking, if you go to small x, the helicity distribution can exceed the spin average. So the difference of two quantities can exceed the sum. This is violation of density matrix positivity. And so, of course, you have unitarity. But my question is, whether in your current approach based on the dipole evolution, density matrix positivity is preserved. And my second question is concerning your the polarized Wilson lines. Isn't it similar to the Wilson line emerging for the Bohm-Aharonov effect for neutrons, which is was studied by the way by Peskin and Lipkin, I believe. So this is my second question.
Okay, let me start with the first one, and maybe it will be better if I don't scribble on the screen, but I'll just share the iPad. Hopefully you guys can see it worked before the talk.
Yeah, looks fine.
Okay, so the first question is whether the polarized PDFs can exceed the unpolarized ones. So the answer is I don't believe so. So what happens is that if you have, say, in a gluon sector, let's look at gluons. At small x, the unpolarized gluon PDF goes as just 1 over x to some power, right? But the power is 1, plus then you get perturbative corrections, right? So at small alpha, you get a series of this type. And that's what you get from solving BFKL evolution. Leading order BFKL gives you the first term, etc. The point is, let's assume that the coupling is small. This goes as 1 over x. What we are talking about is the helicity distribution, which at very small coupling it's subiconal, so it starts not at 1 over x, but at x. So in other words, we can write it as 1 over x to the power of 0 instead of 1, plus some number times square root of alpha s, because of double logs, not single logs. And this is what we've been talking about, and maybe other resummations of G1 structure functions. So this is a double log. And then you have probably other alpha s corrections, etc. So I think what you're saying is that square root of alpha is larger than alpha s. That is indeed true. But what you should be comparing is the entire power, right? So this is 0 plus square root of alpha s times some number, and you compare it to 1 plus some number times alpha s. So your concern of delta G being larger than G can only be realized when alpha is not too small, such as square root of alpha is larger than 1. But of course, in that case, if square root of alpha is larger than 1, the perturbative calculation would kind of be at the edge of its applicability, right? At the very least, you need to calculate high order corrections. So I wouldn't worry too much.
No, I fully agree with you that it's not a practical question. But for example, for Deglop equation, you may prove rigorously that positivity is preserved. Here, I mentioned rather just an academical problem of double logs and log. And it seems to me that what you present now, this your new evolution equation, it seems that it's here also the positivity preservation can be proved rigorously, which is my first some glance. Yeah, this.
So you want to prove something like this, right?
Exactly. That it remains valid all the time. And for Deglop equation, you may prove this just by checking that there is a similar relation between regular parts of evolution kernels, and that singular part is present only in non-flip kernel. So I studied this a while ago. But for this double locks and single lock, there is, I think it's only a problem of principle. Again, repeating in third time, it seems to me that your new equation it's quite possible that it's possible to prove this just rigorously. But it's really preserving this rigorously.
Yeah, we haven't looked into it because, like I said, we were really expecting that at small.
Yeah, sure. Practically,
do you have a reference I should look at? Actually,
yes, I can send it to you. Yes, there is also physics reports review that. So
okay. Now your second question. Sorry, I haven't gotten to
concerning because it remains this polarized fields online remains me what happens. What would happen or happens for Bohm-Aharonov effect with neutrons? I believe that there were some papers. One of I believe was by Aharonov and Kesher, and it was paper by Peskin and Lipkin. And it seems similar. Also magnetic moment matters because neutron is is neutral, but there is magnetic moment. So maybe it's some similarity with that. And sorry, yeah. and because of this, maybe because of this, it's also possible to say something about positivity. This seems to me.
Okay. Yeah. I unfortunately I never looked at the Aharonov-Bohm effect for the neutrons. So my answer to your question is simple, that I just don't know. You might be right, but I haven't looked at those papers. You're saying Peskin and Lipkin.
Yeah. It's I can maybe also this can be interested also for students. Yeah, because it's this is it was some just literature about that. There is quite some papers. Just on this.
But did they have Wilson lines? Well, I guess if it's a Aharonov-Bohm, they did. But it was QED, I guess. It was not QCD, right?
No. Of course QED. It should be just Q. What you have is certainly just different. Yes.
Oh, yes. But they needed to have a magnetic some sort of a dipole moment, right?
They have a magnetic moment of neutron. Because neutron does have a magnetic moment, but not charge. So this is some ice. Just let me.
We have another question, so maybe we could also move on to the next question now. Travis Dorr, you are the next.
Hi, thanks a lot. Really nice talk, Yuri. I was able to follow along for a lot further than I thought I would be able to. I just have a few questions from the perspective of like just a kind of a naive graduate student who works outside of this field. First, I mean, I can ask as many as I have time for, honestly, but the first one would just be kind of broadly speaking, how has the questions that we ask about the proton spin changed over the past few decades? Because it feels like in the late 80s, it was like, okay, well, we have this simple picture of a proton that is made out of these three quarks, and okay, they should add up to 1/2, right? And then I feel like as we started to learn more and more about QCD and about the structure of the proton and about, these RG type flow equations that we have going on, where like you resolve smaller and smaller structure, I feel like the kinds of questions we ask about the spin has changed. So can you like broadly talk a little bit about how that's changed?
Well, so I think you kind of summarized it well, and I may not be quite the right person to describe the entire history, because it's not like I've worked on a spin puzzle for the last 3 decades or something. I've only worked on this for the last 5 to 7 years. I mean, the way it's changed is, I think, what's roughly described in the talk, right? So it started with a constituent quark model predicting, this 2 spins up, 1 spin down thing that was refuted experimentally. I think my understanding before that constituent quark model was rather successful. So people started thinking, well, where else can the spin be? And the sort of the thinking was that the spin is carried by just one dominant source, and maybe experts would correct me if I'm wrong. So it has to be quark spin, or it has to be gluon spin, not like kind of like 4 contributions more or less contributing comparably, but people were looking for like some major source of it. Of course, Deglop was involved in the extraction and all this RG evolution that I mentioned. Perhaps an interesting part of the story, which I didn't talk about, was the contribution of the axial anomaly. So if you look at the Helicity PDF, it's sort of related to well, you can argue, and that's a whole separate story. It's related to an axial current, and then axial current has an anomaly. So actually, if you don't mind, I can switch to a tablet again. So for a while, people thought, yeah, if you could see it now. So axial anomaly. So you can argue that, say, this delta sigma is related to something like q bar gamma plus gamma 5 q, right? Which looks like the plus component of q bar gamma mu gamma 5 q. Q is a quark spinor field. So this is just the axial current. And then there was in the early 90s, I believe, and maybe a little bit late 80s, right after this spin puzzle started, people were thinking, well, maybe there is a contribution, a triangle anomaly. I don't know if you're familiar. You said you're a simple graduate student. The question, there are different shades of simple, but I don't know if you've seen the triangle diagrams like this. Have you or not?
I've seen them before, but I'm not an expert in them.
Okay, so they generate something called an anomaly. Anomaly is when you have a current, for instance, which is conserved classically, but not conserved quantum mechanically, right? So you can define this current. For massless quarks, you can argue that classically this is 0, but in full quantum field theory, you actually get this proportional to ff tilde, where this is a field strength tensor, and f tilde is a dual field strength tensor for the gluon field. Anyway, point is, people were trying to relate this to the anomaly, saying that somehow anomaly, so this is the Helicity distribution. The anomaly affects this measurement that people actually measure. So instead of measuring the quark Helicity PDF, they measure quark Helicity PDF, minus some number times the gluon Helicity PDF. And so they were saying, well, what they measure is this, but what they need for the sum rule is that. But it turned out that to justify this measurement, right, what they saw for quarks was very small. One needed something on the order of 4, a very large coefficient in front of delta G. And my understanding is ultimately it became clear that the anomaly is not able to give such a large coefficient. So that activity kind of stopped at that point, that you cannot account for the missing spin by just some anomaly effects. But this is like, you wanted history, so this is a serious historical part of the spin crisis discussion. But that's pretty much it. After that, more recent events, I guess, a more comprehensive feats. So So comprehensive PDF extractions with Helicity have been done only starting in, I guess, around 2000s, mid 2000s, and I mentioned some of them, like DSSV, and NPDF, and GEM. So like CTEC collaboration and the MRST, for instance, PDFs, they used to be unpolarized, and I don't even know if they do polarized PDFs now, but these guys here did the comprehensive extraction of PDFs, including delta sigma and delta G, and so that happens in let's say 2000s, and that's, I think, broadly speaking, that's it. That's the history. You had the spin puzzle discovery experimentally, people trying to explain it away with the anomaly contribution, and then people using Deglop evolution to do more comprehensive PDF extractions over the first decade of this century, millennium, whatnot, yeah, and that's where we are. Is that what your question was? I'm not sure if I answered it or not.
Yeah, I think that's a good historical perspective on it. I guess one other aspect of that question for me is so the work that you did, as I understand it, was for a given q squared, you go to lower x and you can evolve in lower x, right?
Right.
How does the picture at smaller and small, or as you go, like the evolution as you go to smaller x, how does that change as a function of your q squared that you're starting with?
That's an interesting question. It actually has, all right, so maybe I don't think I have a slide on it, but I should go back to my slide and point at something there. The q-square dependence exists, but it's rather mild. So when I'm writing something something like, just 1 second, let me get to it. I probably can jump over. Nope. Yeah, when I'm writing something like this, right, just a power, right, you say, okay, what's tilde, what's q-square dependence? There is some q-square dependence, but it's rather mild. So something like a log q-squared, the log squared q-squared. So it's not a very strong q-square dependence, it seems, which is a puzzle in its own right. But then we looked at the data, and the data didn't seem to have a very strong q-square dependence actually either. So that was a bit encouraging. So once again, you may have 1 log or maybe 2 powers of log q squared in the prefactor. So something polynomial in log q squared, but no big powers of q squared, it seems.
So can I understand that in an intuitive sense as it doesn't really, so q squared was related to this length scale resolution. I mean, this was the intuitive picture that you gave earlier in the talk, that q squared is related to the length scale that you're resolving over the proton. And so can I understand that as it doesn't really matter what length scale I'm resolving over the proton, as I go to smaller and smaller x, I'm still hitting things that give, similar contributions to the spin?
I guess for sufficiently small 1 over q squared, I guess you could probably say something like this, that it doesn't matter anymore. I mean, it's not true for any small x evolution. Say for unpolarized evolution, for BFK evolution, you do have q squared dependence as well, quite clearly there. I guess it's more like there is some sort of a screening that you stop as you go towards sufficiently small distances, you stop being sensitive to larger distances, and you kind of stay at the same polarized parton, and you kind of measure the same polarized parton. But I'm afraid I don't have a very good intuitive picture for that statement. Sorry, there's only so many intuitive pictures one can generated. It's
Well, definitely it gives you some ideas to think about in the future.
right. Okay, sorry, I know we're running over, so yeah, I'll probably, if I don't have an answer, yeah, I'm not gonna think about it too much. So sorry, Travis, I don't have a good physical
No, that's
intuition for that.
that's fine. Thanks a lot for taking the time.
Sure.
Okay, I don't see any other raised hands, but I do have one sort of very simple, maybe graduate student level question myself. Do you have an intuitive picture why small x region is still contributing such a large contribution to the spin, to the total spin of the proton? Is there some sort of, or it's not really that large in some sense? That's what I'm trying to understand. Is there maybe some kind of intuitive physics understanding why this is the case?
Yeah, so let me say a couple of things. I'm afraid it's similar to Travis's question. I don't have a very clean physics intuition on that. What I may flash is, of course, something you know very well, right? That first of all, there is a lot of stuff at small x, right? I showed this slide a couple of times in my talk. At small x, you have a lot of C quarks and gluons. These are polarized particles, right? So a priori, it's not clear why shouldn't they contribute to the proton spin. Another thing is when we say a lot, right, proton spin is 1/2. A lot is like what we're talking about is maybe 20%, which is 0.1. It's still not a huge number, but as proton spin goes, that's a lot.
Well, I mean, in the sense that x 10 to -3 seems very, very small, naively, and yet there is like 20% of contribution. So somehow,
okay.
I don't know, maybe it's a meaningless question, really, since again, it's what is large, what is small is unclear.
Right. Well, one thing I want to show, and this is what I showed answering Oleg's question, is so yes, a small x. You say that's a very small x, but you have a distribution delta g which explodes as a power of 1/x, right? Okay. We hope that the power and say the net spin of the gluons is an integral dx of delta g, right, from 0 to 1. So you hope that this is an integrable, for instance, singularity at x equals 0, and for smaller than 1 power, of course it is, but it may still contribute significantly, right? And like you said, and I had mentioned before, what's large here doesn't have to be large. It has to be on the order of 0.1, and that's already large. One other thing I briefly mentioned in my talk is once you hit the saturation region, I believe everything will change. So this power law is sort of in the intermediate region of small x, but not terribly small x. So I don't know if you guys had any saturation talks in this colloquium series, but at very small x, we expect non-linear recombination effects to become important, and they will kill all this evolution I'm talking about. So there is some sort of a x sat below which, at least superficially, not doing any hard calculations, I would expect to find very little proton spin. So once you're in that region where the proton is just a black disk, you cannot resolve its spin, and it's not gonna carry any spin that you. So those partons in this black disk don't carry much spin, I guess, measurable spin. So at very small x, yeah, I wouldn't expect anything, but in between, I don't see why not, right? I mean, I really, people are asking, why do gluons carry spin at small x? Some people were okay with quarks, but not with gluons, and I also don't understand why not, because gluons have spin 1, they're polarized, they can be polarized, so they have spin. So why can't they carry spin at small x?
Even simpler, orbital momentum should be definitely carried by everything. It's not a big problem.
This is just circularly polarized gluons, like there are circularly polarized photons. So why not?
No, it's perfectly fine. Yeah. Anyway, Before we wrap this up, I really wanted to use this opportunity still to thank Yuri for a nice presentation.
Thank you.